Hello everyone, I am Zhang Yu from Southwest Petroleum University in Chile. My research interests include the theory and application technology of oil and gas stimulation. I am delighted to have this opportunity to share something with you. Today, we will focus on a unified multiple transport mechanism model for gas through shale pores. My presentation includes the following parts. First of all, I will give a brief introduction to our research background and object. For the second part, I will introduce the specific establishment process of a unified multiple transport mechanism model for gas through shale pores. The third part is model validation. The first part is results and discussion. The last is conclusions. First of all, I will give a brief introduction to our research background. Predicting apparent gas permeability, referred to as AGP, in nanopods is a major challenge for shale gas development. Applied to characterize the shale gas flow regime as a continuous flow, the closest number is 0 to 001. Slip flow, the closest number is 001 to 01. Transition flow, the closest number is 01 to 10. And the free molecular flow, the closest number is greater than 10. Overall, the currently established models are unable to consider a regime mechanism. It is urgent to develop a fully coupled unified single nullable HP model for shale gas, merging with the aforementioned gas transport mechanisms. Notably, three pore types are found in shale purpose matter: inorganic pores and organic pores, and the size of inorganic pores is 20 nano to 4,000 nano. What's more, the size of organic pores is 5 nano to 200 nano by scanning electron microscopy. So we can simplify the shale pores matter to many nanotube per capillary. For the second part, it is methodology, aiming at the flow regimes widely exciting in shale nanopores. We review the transport mechanism of continuous flow, slip flow, free molecular flow, and transition flow, which constitute the bulk gas transport mechanisms. Then we divided shale pores matter into organic and organic pores. For the organic pores, we consider the gas desorption effect and surface diffusion. And for the inorganic pores, we consider that the water storage effect is a unique feature of inorganic pores. Then, for the shale purpose matter, we will consider the stress dependence effects and the river gas effects. Finally, we can get the AGP model for organic or inorganic nanopores. The details as follows. There are four flow regimes widely in shale: continuous flow, slip flow, free molecular flow, and transition flow. First, we use the continuous flow flex model to characterize the continuous flow mechanism. Secondly, we use the slip flux model to characterize the slip flow mechanisms. Similarly, we use the free molecular flow flux and the transition flow flux model to characterize the free molecular flow and the transition flow mechanisms. Then we review the multifactorial effects mechanisms by gas desorption effects, surface diffusion, stress dependence effect, water storage, and real gas effects. The AGP model for organic land pores as follows. We divided the flow flux under each flow regime by this equation. Can get the AGP model for organic land pores, and we consider the stress dependence effects, gas desorption, real gas effects, and surface diffusion. Similarly, the AGP model for inorganic land pores as follows. We consider the stress dependence effects, water storage effects, and the river gas effect. The third part is model validation. We have our presentation model comparison of the model of Essen, Song, and Sean's model. From the figures, the agreement is high. The first part is our results and discussion. First of all, it is methodology, matter, and process. From the figure, the AGP decreased gradually as the pressure decreased and decreased sharply for small pores, notably in the follow transition region. As the follow region transitions from transition flow to slip flow, the AGP in organic pores is greater than in inorganic pores. Secondly, it is real gas effect. The effect of real gas has a dramatic influence on the inorganic pore AGP calculated by the ideal gas model under pressures lower than 30 MPa but for per size of 20 nano. But it is 22 MPa for a per size of 2 nano. Thirdly, it is water storage effect. From the figure, we can know something. For a small pore size at the critical high water saturation, the AGP might increase suddenly as the flow regime changes from continuous flow to slip flow. The next one is conclusions. First, the AGP decreases gradually as the pressure decreases, but that the decrease is sharp in small pores. The AGP decreases dramatically when consider the real gas effect at 50 MPa in a 2 nano pores size. Thirdly, for a small pore size at the critical high water saturation, HP might increase suddenly as the flow regime changes from continuous flow to slip flow. Additionally, these research are supported by the Structural Science and Technology Plan project and the National Key and Development Program of China. The above is all the content of my report. Thank you for your attention.